Okay, so my name is Vikas Kumar Singh, and in this session we are going to solve the assignment number 2 for the NPTEL course which is going on online on SWAM website, sheet metal forming, mechanics of metal forming. So, um, as we know, like this course was designed to discuss the concept which is professor is teaching online. So here it's like a live interaction, and interaction is recorded for uh, uh, for your convenience or reference also that people can see online. So now we are going to discuss the assignment number 2 and then concept related with the assignment number 2, whatever is there, all everything we are going to discuss here. Okay, so assignment number 2 is mostly related with the concept of failure theory, one Mises criteria, Tresega criteria, and all. So mostly the question will be from the one Mises criteria of yielding and all. So somewhere some question will come from the one Mises criteria. So we'll try to understand first the one Mises criteria, and then slowly we'll move forward according to the question. So here is the first question in assignment number 2, which we are going to discuss. So here it is given the stress state in a metallic billet is described by the principal stresses 100, 150 to 200 megapascal. So here the things are given principal stresses. So principal stresses we are denoting sigma 1, sigma 2 and sigma 3, and they are given is 100 megapascal minus 150 megapascal, and the third one is 200 megapascal. Okay. So minus means compressive stress is there in direction number 2. If the body reached plastic state, what would be the find out the yield strength in the tension. So using one Mises yield criteria. So one Mises, I will try to explain what is one Mises first, and then we will calculate it. So in the one Mises, like we'll start with the basics of this thing, one Mises. So if you have any kind of material, any kind of solid material, and you want to deform this material, suppose this is a cubic shape material, and you want to deform this material, you want to increase the length, width, or something like some. I'm just giving one example to understand this thing. So the thickness was more, and now thickness has been reduced, so that we are putting some load, suppose like this. Okay, so this is just a deformed shape of this. So material is deforming like this. So if you want to deform a material, you need to put some amount of energy in the system, some amount of energy in terms of stress or stress and strain. So if you are putting energy, then this will deform. So whatever energy you are putting, that energy is having two part. One is distortion energy and one is hydrostatic. So some amount of this energy is going to distort the material, and some amount of the energy is going to change the size of the material. So this is called hydrostatic, and this is called distortion. So when we are giving some amount of energy, one part is distortion and one is hydrostatic. So hydrostatic means simple. Suppose you have suppose a circular disc is there. So from each and every side, all the direction, you are putting same amount of pressure to the material. So what will happen? This disc will, or sheet plate will shrink in the same size. Whatever size was there, same size is there, but just dimension has reduced now. So diameter is low. or if you have a disk like this and you are pulling from all the direction, you are applying same amount of stress in all the direction, then what will happen? This will diameter will increase. So this kind of loading is called hydrostatic. So hydrostatic does not change the shape. Whatever shape is there, that shape will remain same, and distortion will change the shape. So is this will keep the shape same, and this will change the shape. Change the shape. Okay. So this part will, suppose we have like this circular disc was there, so this energy can make this type of shape. So this is nothing but the distortion. So all the energy is going in two part, and this part is associated with one Mises yielding criteria, one Mises. And so suppose if we are able to remove this amount of energy from the total energy, so we will get the distortion energy. So, and energy density is nothing but E by volume, whatever volume is there. So this is generally denoted by U. So U total equal to UD plus UH. This is hydrostatic and distortion. So this amount, if you will derive this thing, so you will get UD value, and this UD is nothing but it's going to be 1 by 12 G. In term of, I'm writing in term of G, you can write in term of E also. G is your shear modulus, E is Young modulus. So, and this will be sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square. This will be the value. So if you are able to change this 12G, so instead of 1 by this, if you want to include E means Young modulus, this will come 1 by 6E. Okay, so this will come like this. So we know this. So now from this energy, we have to find out what is the yield stress yield stress using the one Mises criteria. So if you have gone through the lecture, so yield stress is, if you yield stress is coming, this formula is coming. I will tell you from where this is coming. This formula, sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square. And this is like this. How this will come? So suppose if somebody is asking yielding and equivalent, yielding or effective or equivalent stress, so definitely we are considering uniaxial loading. What will be the effective uniaxial tensile yield point or uniaxial yield point, so that material will deform? So in such situation, what we have to do? Nothing. We have to just replace sigma 1 with the sigma y. And if we are talking about the yielding of uniaxial, sigma 2 and sigma 3 will become 0. So if you will put this value in this equation, you will get UD in term of yield. And now this equation you just equate with this, and then you will get this equation. And this is already derived in the lecture, so you can just see that thing. So I'm just trying to solve this problem. So this is the formula. Now if you are going to put all this value, then you will get here, if you are going to put all this value, you will get 100 200 minus 100 to the whole square plus 100. What is that? Sigma. We are okay. Here I have written sigma 1, sigma 2, sigma 3. So we can write here sigma 1 is the 100, and this one is the minus 150. Okay, and this value is nothing but sigma 2 is minus 150 and sigma 3 is minus 200. Sigma 3 is 200 minus sigma 1 is 100. Okay, so this value will come, this value becomes 100 square, this value become 350, 350 square, and this value become 50. This value become 100 minus, this is the minus, so minus minus plus, this will become, because this is 150 is here minus, so this will become 250, 250 square, and do this 1 by 2. So this will give sigma y square. So if you will solve this, sigma y will nothing but 1312.4 megapascal. So this will be the value. Okay. So the what is the concept here? You just have to derive this formula from the total energy theory, and then you will get the distortion energy, and from the distortion energy, how you are going to get the yielding criteria. Now we have question number 2. And this is similar question as we discussed in the first, like one Mises criteria is here also. So one Mises criteria, as we know, we have derived this formula sigma y square equal to 1 by 2 into sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square. This formula is there for the yielding in the case of one Mises. Okay. And here one formula is given for the effective stress. This is nothing but this formula. Okay. So this one is given here, and this formula is sigma effective equal to 850 epsilon effective to the power 0.2. This is not minus 0.2. This is epsilon. Bar is the effective strain. Okay. So now in the question, they are saying 1 mm thickness sheet is there, and we are deforming that sheet using this power. Okay. It is deformed in a drawing mode following the strain ratio. So what is the strain ratio that we have to write it here? Strain ratio is sigma epsilon 2 by epsilon 1. So this is given here equal to -1. Okay. Now, a square element of 10 mm into 10 mm dimension aligned with the principal direction is extended to 12 mm on same side. So, okay, let me draw a sheet of some certain width and length and some 1 mm thickness. This is the sheets, or this is, you have sheet. Okay, one square strip is there over here. Suppose this is 10 and this is 10. So we are focusing over here only, this part. So this part is elongated, and now this became 12. This became 12. This became 12, and this will reduce. We don't know how much this value is right now. So this became 12. Okay. So now they are asking in the question, calculate the effective stresses, assume the sheet follow the one Mises criteria. So if we have to find out how much strain is there in in this direction, that strain is nothing but that is true strain, nothing but ln final length by initial length. So this will be the strain in this direction. I'm just denoting with 1, and this value is nothing but 0.182. Okay, this is okay. Now here it is given beta equal to -1. It means epsilon 2 equal to minus epsilon 1. So here we will get epsilon 2 equal to minus 0.182. Okay, this is the, and the third thing is epsilon 3. So we know epsilon 1 plus epsilon 2 plus epsilon 3 equal to 0 plus plastic deformation. So from here, epsilon 3 will be minus of epsilon 1 plus epsilon 2. And this value is nothing but this is going to be 0. So here epsilon 3 equal to 0. Okay. Now we have to find out the effective strain. So according to the von Mises criteria, effective strain is nothing but 2 by 3 epsilon 1 square plus epsilon 2 square plus epsilon 3 square. This formula you can check the derivation, you can see the derivation, you will get it. So if we are putting all the value here, we will get 0.2102, and this is the effective strain here. Now, what is the effective stress? So effective stress is nothing but 850 into, here we are putting effective strain, this value is 0.2102 to the power 0.2. And this value is going to come 622.1037 megapascal. So they are asking calculate the effective stress, and this stress value is this. So in this question, what is the logic? How we are going to approach this? So we had this formula, this power law was given, and effective stress, only this formula you have to know for this thing. So one should know this formula and the derivation to solve this question, from where this is coming according to von Mises criteria of strain. So the concept was, we know epsilon 1. I just took length direction is 1 and width direction is 2 and thickness direction is 3. So suppose this is the sign convention for principal stress or principal strain. So epsilon 1 we got from here, epsilon 2 we got because this beta was given. Beta is nothing but the strain ratio. Beta is a strain ratio. And from the volume consistency, we got the epsilon 3. Once we got epsilon 1, epsilon 2, epsilon 3, then easily we can find out what is the effective strain. And then using the effective strain, we can find out this value. And this is coming this much. Okay. So now we are going to the next question. And here we have a next question again. And this is very interesting question, because again we are using the von Mises. So if you are seeing all these things, so you might have noticed you might have noticed everywhere where von Mises criteria is coming. So you must know all the derivation of the von Mises. So in short, I will just write von Mises is coming from the strain energy theory. So suppose you have total strain energy equal to half into stress into strain into volume. Okay, so from here this is having two component. One is E distortion and one is EH. So if you, when you are going to find out EH, or when you are going to find out ED, whatever is, so you have to take the account of, in case of hydrostatic, the sigma 1, sigma 1 will be sigma 2 will be sigma 3, and this will be sigma p, because hydrostatic pressure in all the direction this is same. So you just consider in case of hydrostatic sigma p for all the principal stresses, and for sigma total energy ET, you can find out from stress and strain, and from how you will get this value. So this you are going to get it 1 by 2 sigma 1 epsilon 1 plus 1 by 2 sigma 2 epsilon 2 plus 1 by 2 sigma 3 epsilon 3. This is per unit volume, per unit volume. So we are calculating per unit volume. And now if you are going to put all the value of epsilon 1, epsilon 2 and epsilon 3, then this will give a formula for total strain energy. If you are going to put all the value. So what is that all the value? What all these things are there? So epsilon 1 means sigma 1 by E minus nu by E. Nu is the Poisson ratio here. Sigma 2 plus sigma 3. Similarly, you will get epsilon 2 and epsilon 3 and replace all this value in this equation, then you will get the final equation what we wrote here in this thing. Where, yeah, total energy formula we wrote here, this formula here, 1 by 12 G, this formula. This is the distortion energy, sorry. So, okay, we have not written this formula, we will write. Okay, so if you will replace all this thing in the equation, you will get the final formula for this thing. And this is nothing but your uh, total strain energy, and we can easily derive this. So total, okay, I'm writing UT equal to 1 by 2 this, and you have to replace here this one with sigma 1 by E minus nu by E into sigma 2 plus sigma 3. Okay, plus this is done. And next part is 1 by 2 sigma 2, and here it will be here this value is this epsilon 2, and this is going to sigma 2 by E minus nu by E sigma sigma epsilon 2. Yeah, here we are going to write epsilon 2 by E minus nu by E 1 plus 3, and this value is going to be sigma 3 by E minus nu by E, and this value is sigma 1 plus 2. Okay, this is 1 plus 2, this is 1 plus 3, and this is 2 plus 3. So sigma 2 is epsilon 2 value. If we are just replacing this value over here, so this is going to be sigma 2 by E minus nu by E into sigma 1 plus sigma 3 plus 1 by 2 sigma 3 by E minus nu by E into sigma 1 plus sigma 2. So this is your total energy, total strain energy. And now if you will replace sigma 1, sigma 2, sigma 3, all these three with the sigma P, you will get total hydrostatic. And once you will get this value, just subtract this value from here. Total energy density minus hydrostatic, you will get UD. Okay, so once you will get UD, then what you have to do here, UD will give the condition for effective, yield strength, yielding point. This will give the condition for yielding. Okay, so for getting the yielding condition, what you have to do, once you will get UD, just replace sigma 1, sigma 2, sigma 3. This will become, for uniaxial tensile, this will become 0, and just replace this with the sigma y. Okay, so you will get this condition. So this value is going to be sigma y equal to, I'm just writing like this, sigma y square by 1 by 2 into sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square. So this is the final condition what we are getting after solving all this equation. This is the final. This is the condition for yielding. Okay, this is the yielding condition. Now, in the question, few things are given. First one is a yield criteria that we have derived. Sheet metal deformation under plane stress and plane strain. In plane stress, we are talking sigma 1 and sigma 2. Sigma 3 is equal to 0. Okay. And with a flow stress, and here flow stress is given. This flow stress is nothing but your yielding point only. Okay. Yielding. After yielding, all the stress is flow stress only. And incompressibility. So if you are knowing the meaning of the incompressibility, it means bulk modulus is going to be infinity, and this will give a condition Poisson ratio is 0.5. If you don't know this, just go to the textbook and get it, this value. Incompressibility means new Poisson ratio is 0.5. So so after that, they are asking what is the value of sigma 1 by flow stress, sigma 2 by flow stress, sigma 3 by flow stress, and this is the strain ratio, and this is the strain in third direction and second direction. Okay, so now we have this formula. So we'll do we sorry. So we have in the previous section we have derived this formula here. So for the plane stress condition, I am just writing sigma y square equal to sigma 1 minus sigma 2 whole square plus sigma 2 square plus sigma 1 square. And this is going to be 1 by 2. Why sigma 3? Because in the plane stress, sigma 3 is 0. If you will solve this, you will get sigma y equal to sigma 1 square plus sigma 2 square minus sigma 1 sigma 2. If you will solve this, you will get this. I am just removing this square. How this will come? So this is a minus b to the power b to the power 2 means a minus b whole square. So sigma 1 square plus sigma 2 square will come, and here already 2 are there, so it will become 2 sigma 1 square in plus 2 sigma 2 square, and 1 2 will come in this one. 2 sigma 1 sigma 2 will come minus, so this 2 will we will take common, and this will be cancelled with this 2, and this will be remaining. So this is the final final equation for the yield stress in case of plane stress condition for one Mises criteria. Okay. Now, the question is that they are asking what is the value of epsilon sigma 1 by sigma f. This value, what is this value? And then what is this value? Okay. And then what is beta? And then 3 by 1. This all value we have to find. Okay. So now for yielding means plastic deformation, we have plastic deformation principal stress ratio assumption. In the plastic deformation, case of plastic deformation, in the case of plastic deformation, we have principal stress ratio assumption, and that assumption is nothing but sigma 2 equal to sigma 1 by 2. So once you will put this one in this equation, you will get, and now I am writing instead of sigma y, I am writing now sigma f because flow stress I am taking. So if you will put this will be sigma 1 square plus sigma 1 square by 4 minus sigma 1 into sigma 1 by 2. Okay. And this will be like this. Okay. Now we have sigma 1 4 okay, 4 sigma 1 square plus sigma 1 square minus 2 sigma 1 square divided by 4 to the power 1 by 2 means root. So this is going to be what? How much? 4, 5 and minus 2. So 3 sigma 1 square by 4 and root under. So this is going to be root 3 by 2 sigma 1. This is the sigma f. So what is the ratio? So then the ratio will become sigma 1 by sigma f will become 2 by root 3. So this value will become 2 by root 3. Similarly, sigma 2 is nothing but 1 by 2 of sigma 1. So 1 by 2 means this will become 1 by root 3. And now what is the sigma 3? So obviously sigma 3, this will be 0 because already we have considered this value. Okay. And now beta is what? Beta is epsilon 2 by epsilon 1. Okay, so we have to find out what is the epsilon 1, epsilon 2, epsilon 3. So epsilon 1 is nothing but sigma 1 by E minus nu by E into sigma 2 plus sigma 3. So what is this value? So this value is going to come, like we have found out here. From here you can see sigma 1 is going to be 2 by root 3 into 2 by root 3 into flow stress. Okay, so and this is nothing but 0. So this is nothing but 0. And so final value sigma 1 will become how much? Sigma 1 will become sigma 1. The value I am putting here, that value is 1 by E. I am writing, I am taking the common, and sigma 1 is there. So sigma 1 is 2 lowest 2 into flow stress divided by root 3. Okay, root 3 is the sigma 1, this value. Okay, yeah, and minus what is that? Nu. So minus nu, and then you have sigma 2. So sigma 2 value is flow stress divided by root 3. So flow stress divided by root 3 here. And now, once you will put nu equal to 0.5 in the equation, as initially it is given in the equation here, this value, so you will get the epsilon 1 value directly. So this value is how much it is going to come. This value, if you will solve this, this value will be root 3 by 2 into epsilon f by e. This value you will get. Okay, and what about the sigma 2? So sigma 2 is nothing but how you will get, sorry, epsilon 2 is nothing but sigma 2 by E minus nu by sigma 1 by E, and sigma 3 is 0. So we'll neglect that. Okay, so we have this value and we have this value. Okay, so you once you will put the all the value, like sigma 1 value, you will put root 2 by root 3 into epsilon f here, and here you will put sigma f by root 3, then you will get all, after solving you will get a 0. Okay, and epsilon 3 is nothing but we have minus nu by E into epsilon 1 plus epsilon 2. Just put all this value, this value is coming from here, okay, and here. So you will get minus of root 3 by 2 flow stress by E. Okay, so you got this ratio. Now what is this ratio? This ratio will be 0, because why? Because this is 0, and the 0 by this value will become 0. And this ratio, how much? This is going to be just this, it is the same value, whatever it is coming here, just with the negative sign. This will become minus. So we solved this problem. So now what was the thing what we should consider here? So we considered, like, first of all, it was the plane stress condition, plane stress condition. Plane stress, in this one we consider sigma 3 equal to 0, and then in this condition plastic deformation is there, so this should also be applicable. So you can check this is applicable or not. This will be equal to 0. So yeah, sigma 1 and 3, it's opposite sign, same value, and this is 0. So this is also 0. This is applicable. Okay, and then we, one more assumption we used. That assumption was, in the case of plastic deformation, the principal stress ratio assumption is nothing but sigma 2 equal to sigma 1 by 2. Okay, so this one was the one of the assumption. So this question is completed. Now we are okay. Anything else in this question? We will just read. Any other things they are asking or not? No, it's solved. Now coming to the next question. Yeah, this question is very easy, and this, if you have gone with the lecture, so you might have seen the Levy-Mises criteria, and Levy-Mises criteria was given. Levy-Mises criteria. And if you have gone through this and one Mises criteria, actually one Mises is not that much related. Only here we have to go with the Levy-Mises criteria in the PPT, if you have seen the lecture. So you will find their alpha and beta. And this is nothing but your stress ratio, and this is nothing but strain ratio. So they are asking in this question, it is to be it is asked like what will be the relation between these two. So stress ratio is nothing but your sigma 2 by sigma 1, and this is nothing but sigma epsilon 2 by epsilon 1. And keep this thing in mind whenever we are writing 1, 2, 3, all we are talking about the principal stresses or principal strains. When we are writing x, y, z, it's not principal stress or principal strain, it's a general case, general state of stress. Okay. So once you will go through this and you will derive all these things, so you will get the relation between stress ratio and strain ratio, that is 2 plus beta. This derivation, if you will check 2 plus beta into 2 beta plus 1, this is the derivation. And from here, if you will solve this, you will get 2 beta plus 1 divided by 2 plus beta. So this is the relation between the stress ratio and strain ratio, and this is the correct option for that. So this is already derived. So this is objective question, so it's no point to derive it again here because already it is there derived in the lecture. If you have gone through the lecture, theoretical lecture, yeah. Now here we have next question again from the one message. So one can notice every time we are discussing one message, definitely other failure theories are there like principal stress criteria, Tresca criteria, principal strain criteria, all criteria are there, but most of the time we are discussing one message here because one message is very important for ductile materials. And mostly whenever we are talking about the design and all design of some component, uh, we cannot ignore this theory, this failure theory, because ductile material is very much suitable. So we are again coming to the one message yield surface is of which shape. One message yield of which shape. So in 2D case, if you have seen in 2D case, like this formula, if you are remembering, square plus this minus sigma 1 sigma 2, this was the case of plane stress. This was the case of plane stress in case of one Mises criteria. So if you consider this one and this one as a two variable, sigma 1 and sigma 2, so this is nothing but the equation of ellipse x square plus y square minus xy equal to, and this is the constant value. So I am just taking some value, suppose constant means r. So this is nothing but a ellipse. So this is going to be something like this. This is sigma 2 and this is sigma 1. Okay. So this is in the case of plane stress. What about in the case of 3D? We have sigma 1, sigma 2, and sigma 3. So in that case, we had this equation 1 by 2 sigma 1 plus sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square. Okay, now you are going to generate a 3D surface with some volume because we have three variables, sigma 1, sigma 2, and sigma 3. So in this, if you are going to plot this equation, so you will get a 3D surface with cylindrical shape. This is going to be something cylindrical. Okay, this is going to be cylindrical shape. This is sigma 1, suppose this is sigma 2 and this is sigma 3. So this is going to be cylindrical shape like this. So this plot for the 3D is cylindrical, and on the cylinder, if you will see everywhere, this is nothing but a one circle, another circle like that. So for different state of stress, you will get the different condition. Okay, so here this option will be there, right circular cylinder for this. Okay, so coming to the next question. And here the next question is asked on the deviatric plane, one mice's yield surface will be like what? Deviatric stress. So deviatric plane means nothing but this deviatric is the another name for the distortion energy theory. So when we just plotted this condition for 3D case, just plotted this one. Suppose this is 1, this is 2, and this is 3, and this one is the so suppose this one is the sorry, yeah. Yeah. So suppose this is the surface which we just drawed in the previous previous slide. So this was the surface. Now in the deviatric plane, one mice's yield surface will be like a what? So at suppose you are going with this point, so this will be nothing but like this. Okay, this surface for at each cross section. So this is nothing but in a deviatric plane, and deviatric plane means you are removing what? Hydrostatic stress. You are removing this part. So when you are removing this part, it means there is no component of this thing, mean value of this sigma 1 and sigma 2. So if you want to remove this from the total energy, means total energy density, I'm writing UD, and you are just removing the effect of UH, then you will get only UD. So in this case, this value become 0 when you are talking about the deviatric, means distortion. Deviatric means nothing but your distortion. So in this case, this will be 0. It means you have removed the hydrostatic component of that energy. Hydrostatic component you have removed. You have only deviatric, means distortion. So in this case, this shape is nothing but circular shape. If you will see from here, not from here, okay. If you will see from here, this will be circular shape. Okay. So now coming to the next question. And yeah, again, this next question is very exciting. Like again, one Mises criteria. So you might be thinking only one Mises is coming. So you can just notice how important this one Mises criteria is. Again, here it is written uniaxial tension, uniaxial. So uniaxial means you have sigma 1, sigma 2 is not there, sigma 3, sorry, sigma 2 is 0, and sigma 3 is 0, uniaxial. One Mises effective stress. Okay, so just let us solve for plane stress condition what we derived. This one, this formula was there for the plane stress. This one is the formula for yielding condition for the plane stress in the case of one Mises. So plane stress means we have biaxial. Plane stress means biaxial. We have sigma 1 and sigma 2. But here in the case of uniaxial means we have to remove this one also. Okay, so suppose in this case we are removing this one sigma 2, so we have only this part. So what will happen now? Sigma y equal to sigma 1 squared. This will become 0, this will become 0, and this is the root, and this will give this value sigma 1 only. So the effective stress means yield stress, nothing but effective. This is sometimes it is called yield, sometimes it is called flow also, flow stress. So just don't confuse. Once yielding is started. After that, whatever stress will come, all are flow stress only after the yielding. Before yielding, it's elastic stress. So we are talking about the plastic deformation. So we are always in this zone, here, in this zone. Okay. So this will be the effective stress. This one. I hope this is clear. And now we are moving to the next question. And the next question is intermediate principal stress does not appear in Okay, so again, if you will see in the case of one message, it is written already here. Correct answer. One message, we have effective stress means effective, or you can say yield or flow, whatever. This value is here, and this value is sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square. This value is there, and I'm just taking a square over here so that we cannot put here a square root. This value. Now, here you can, if you will solve this thing, you will get, there is direct effect of sigma 2, means we have sigma 1, sigma 2 and sigma 3. So this is the intermediate one, intermediate between sigma 1 and sigma 2. So there is direct effect of sigma 2 in this equation. Even for plane stress, if you are converting this, so plane stress, you will get sigma 1 square plus sigma 2 square minus sigma 1 and sigma 2, and this is nothing but this value. So you can see here there is a direct effect of sigma 2 in the equation. Direct means if you will change this value, this will directly affect this yielding point. But in case of Tresca, what is the yield condition? So yield condition is the max of absolute value of sigma 1 minus sigma 2 by 2, sigma 2 minus sigma 3 by 2, and sigma 3 minus sigma 1 by 2. Max of this, whatever maximum value, which whoever is the maximum among these three will be the yield criteria for this. So here we are taking difference. You can see sigma 1 minus sigma 2. Here sigma 2 minus sigma 3. Here sigma 3 minus sigma 1. So intermediate stress means sigma 2. So this part is there in this equation, but it's a difference. There is no direct this thing. So this difference is there. So there is no direct effect of sigma 2 and all. Only difference will play a role. So that's why does not appear in intermediate principal stress, does not appear means Tresca, does not appear means there is no direct effect. It means this. Okay. Now the next question. The next question is here. I think this is the last question for today. The stress state in a metallic billet is described by three principal stresses and 100, minus 150 and 250. If the body reached plastic state, find out the yield strength in shear as per the Tresca condition. Okay, just now we saw Tresca condition is for yielding is the max of sigma 1 minus sigma 2 by 2. This line is giving the absolute value, and sigma 2 minus sigma 3 by 2 and sigma 3 minus sigma 1 by 2. Okay, this is the condition. Now we have sigma 1 equal to 100, sigma 2 equal to minus 150, sigma 3 equal to 200. Okay, so which one will be the maximum? If we are taking this value, so how much it will be? So sigma 1, if I am taking 100 minus plus 150 by 2. So this is the one value. What will be the second value? Sigma 2 minus 150 minus 200 by 2, and this is the absolute. Okay, and the third one is 200 minus sigma 1. Sigma 1 is 100, okay, by 2, and this is absolute. So this is absolute. Okay, this is going to be give how much? 100 by 2, and this is going to be how much? 350 by 2, and this one is going to give how much? 250 by 2. So this is one is the maximum value. So this is nothing but 175. Okay, 175. So as per the find out the yield strength in shear. So yield strength according to the Tresca is this much. Yield stress according to the Tresca. But what in case of tensile? So tensile, this formula is nothing but I'm just writing here T is nothing but here if I'm writing S. So here it will be 2 times of this value S here. So this will give 1 into 175, 350 megapascal. So this will be the answer. Okay. So I hope this is clear. So for today we will stop, and we'll see the next assignment in the next class. We'll solve it, and in the also we can discuss in the next class whatever doubt you have. So we'll stop it now here. Thank you for attending.